Good afternoon, class. Here's elementary statistics, practice test number 4, module 4, covering chapters 8 and 9. Here's chapter 9, inferences from two samples, part 2. Again, a pledge. I'm reminding you when we take the exam, I pledge on my honor that I will neither give nor receive unauthorized assistance, so on and so forth. You may use formula sheet, tables, and a graphing calculator. Test the claim that weights of male college students have a larger variance than female college students. Use a significance level of 0.05 and assume the populations are known. So with alpha 0.05. So what are we going to use? F-test. For the comparison of two variances or standard deviations, an F-test is used. The F-test should not be confused with the chi-square test, which compares a single sample variance to a specific population variance. And again, just like chi-square, it's skewed to the right and it only has positive values. Characteristics. The values of F cannot be negative because variances are always positive or zero. The distribution is positive skewed. The mean value of F is approximately equal to 1. The F distribution is a family of curves based on the degrees of freedom of the variance of the numerator and the degrees of freedom of the variance of the denominator. So F is S squared over S squared. Normally, we choose the two groups such that the larger one is at top because we want to make it right tail test because of the limitation of the F-test. In most cases, unless otherwise mentioned, the F-test has two terms of the degrees of freedom, that of the numerator, n sub 1 minus 1, and that of the denominator, n sub 2 minus 1. So it is skewed to the right. F, first we have to know the alpha because there are different F distribution tables for different alphas. So this is F of 0.05, that means the choice of alpha is 0.05, and then you put degrees of freedom, 1, degrees of freedom 2, that means for the numerator and the denominator. So here's the table. At top, you see degrees of freedom for the numerator, the top row, and the left column, df2, the degrees of freedom for the denominator, and this one specifically is for alpha of 0.05. Okay, it's important to know there are different tables. As an example, if we want to find f of 0.05, so we have chosen the right table, degrees of freedom 10 and 4. So at top here, the first degrees of freedom for the numerator must be 10, so we're going to locate 10. Then 4, the first column, we're going to locate 4 degrees of freedom of the denominator. And when we look at their intersection, the answer would be 5.9644. This is with more decimals. So again, depending on the limitation of the table. That's how you do the reading. So let's actually go back to our question. So same question, and now the information is here for males, for females. Notice S is larger for males than for females, so we choose this one to be the first group. Therefore, we're going to call this N sub 1 equals 31, S sub 1 equals 28, X1 bar, we don't need it. N sub 2 is 29, X sub 2 bar is 125, S2 is 25. All right, and alpha has been chosen as 0.05. There are different ways of writing this. So I'm going to write all of them, and I'm going to discuss the concept. H0 sigma 1 squared equals sigma 2 squared. If you go with that, then we want to see if it's larger, so sigma 1 squared is larger than sigma 2 squared, which makes it a right tail test. and it's a claim. Always make it so. And you're done here. You don't have to write this too. But equivalent to this would be sigma 1 squared over sigma 2 squared equals 1. Sigma 1 squared over sigma 2 squared is larger than 1. Or sigma 1 is equal to sigma 2, sigma 1 is larger than sigma 2. Which one do you use? Just be consistent. Don't mix and match. And if you're given one of them, choose accordingly. See whether they're going to give you sigma or sigma squared. So having said that, that's the first step. The second step is the test statistic. F is S1 squared over S2 squared. And again, we have the given. So 28 squared over 25 squared. Again, by choice, we put the larger one at top. That's how we choose the groups, and 1.254. Now, the third step is the critical value comes from the choice of alpha, which is 0.05. And we have 2 degrees of freedom. For the numerator, n1 minus 1 makes it 30. For the denominator, n2 minus 1 makes it 28. So now, using the table in the previous page, we have the F table, specifically alpha must be 0.05. And at top here, we look for number 30 and the column 28, and the intersection gives us the result for the critical value. F is 1.8687. So having said that, we do the drawing. So the critical value and alpha of 0.05. Test statistic is 1.2544, way into the non-rejection region. So it's easy to make a decision, fail to reject the null hypothesis. So fail to reject the null hypothesis because the value of test statistic falls in the non-rejection region or is smaller than a critical value. Now, to elaborate on that, we go back, and if we are not rejecting H0, that means we are rejecting H1, the claim becomes false. And we restate as follows. There is not sufficient evidence to support the claim that weights of male college students have a larger variance than female college students. As far as the technology is concerned, we may use two-sample F-test, and we put the information S1, N1, S2, N2, and this is larger than. When we do that, here's what it gives us. Again, as chosen sigma 1 larger than sigma 2. Notice this number. This is the test statistic. F is 1.2544. And what is this one? The p-value of 0.275, which is larger than alpha of 0.05. Same decision. Directional asymmetry, or short DA, is a phenomenon whereby in a population, one side of each organism is consistently larger than the other, i.e. left larger than right or vice versa. And evolutionary biologists study DA measures the length of the left and right wings of a sample of Drosophila, a type of flies whose members are often called small fruit flies. Collected from nature, and she gets this data. This is the data. So we have so many here, 17 pieces. The left side in millimeters, 1.34, and the right side in millimeters, 1.26. The researcher decides to perform a two-sample t-test to determine whether the mean wing differs between the left and right side of these flies. What type of t-test will she do? Alpha is 0.05, and part B, find the 95% confidence interval for the difference between the mean. Of course, we are going to use the paired t-test, and we're going to go over that in the next page. I want to remind you what that means. And so we need to calculate the mean, the standard deviation, and so the mean and standard deviation of what? D, the difference. So this one, if we go with L minus R, the first one would be 1.34 minus 1.26, which is 0.08. The second one would be 1 minus 1.28, which makes it negative 0.28, and the rest of it. So we calculate the D, the difference between the two. You can go with left minus right or right minus left. It doesn't make any difference. So we are going to calculate the D. We did that. Now we are going to calculate the mean and standard deviation. Reminding you, remember X bar is summation of X over N. So D bar, the difference, is summation of D over N. Practically the same thing. A standard deviation, remember, is summation of X minus X bar quantity square over N minus 1. We're going to use D minus D bar, and so forth. By the way, sometimes in some texts they use lowercase d, sometimes they use uppercase. And so if we run a calculated process, stat edit, we're going to clear both lists, L1 and L2. Okay. And we're going to put this in L1, this in L2, and we are interested in L1 minus L2. That gives us the third column, the D column. And we store it in L sub 3. Now we run the 5-number summary stat. It gives us D, and on purpose, I use lowercase here, uppercase here, meaning they are interchangeable, which is not the case in math. Lowercase and uppercase have a different meaning, but over here, depending on the text, S sub D is 0.2283, and N, of course, we already know it's 17. We have 17 pieces. So what is a pair t-test? 2 means 2 dependent samples matched pairs. Key concept. Testing hypotheses and constructing confidence interval involving the mean of the difference of the values from 2 populations that are dependent, in the sense that the data consist of matched pairs. The pairs must be matched according to some relationship, such as before and after measurement from the same subject. Good experimental design. When designing an experiment or planning an observational study, using dependent samples with matched pairs is generally better than using 2 independent samples. Hypothesis test. Use the differences from 2 dependent samples, matched pairs, to test a claim about the mean of the population of all such differences. Confidence interval. Use the differences from 2 dependent sample match pairs to construct a difference interval estimate of the mean of the population of all such samples. The individual difference between the 2 values in a single match pair. Mu sub D, mean value of the differences D for the population of all matched pairs. D bar is mean value of the differences D for the paired sample data. S sub D, standard deviation of the differences D for the paired sample data, and N is the number of pairs. When the values are dependent, do a t-test on the differences. In other words, the same t-test that we've done for one sample, we can do exactly the same thing. That's really the same concept. Denote the differences with the symbol D, or lowercase or uppercase D, the mean of the population differences between mu of D or mu of uppercase D, and sample the standard deviation of the differences with S sub D. So degrees of freedom is n minus 1. Use either or, summation divided by n. This is the t. I hope you remember t is x bar, just to remind you. Remember t is x bar minus mu sub x bar over s of x bar, or s over square root. Okay. So now instead of x bar, you go with d bar, and this is the rest follows. And over here we have x bar plus minus E, so it's D bar. It's the same thing. If you call the dx bar, it gives you absolutely the same. So having said that, let's finish the job here. We have this and the information from the previous page. We have the average, we have the standard deviation, we have the size and alpha. So let's do the math. H0 mu sub D equals 0. And H1, whether or not they differ, mu sub D is not equal to 0. Right away, it makes it a two-tailed test. And that's what we are checking. So that becomes a claim as well. Test statistic, D bar minus mu of D bar over S sub D over square root of N. So just from here, plug in. And that's why the given really is important. Again, this comes from H0. You can ignore it, becomes always 0, at least for us. Negative 1.636, so that's test statistic. Now we need the critical value, comes from the choice of alpha. Degrees of freedom is n minus 1, 17, minus 1 or 16. And using a table, we end up with plus minus 2.120, or you can use technology. Notice as far as the always graphing is concerned. So this is alpha over 2, alpha is 0.05, so this is 0.05 divided by 2 on each side. This is negative 2.120, this is positive 2.120, and test statistic, negative 1.636 is in between, way into the non-rejection region. Therefore, your decision is fail to reject is H0 or don't reject H0. Let's go back to the first step. So every calculation is about answering this part. The rest is up to us. So where did we put the claim here? If you're not rejecting H0, you're rejecting H1 and the claim. Therefore, it becomes false. And we write, there is not sufficient evidence to support the claim that the mean wing differs between the left and right sides of these flights. So she cannot conclude that this population possesses dA because the mean lengths of the wings on the left and right sides do not differ significantly. And as far as technology, you can go with matched t-test, t-test data, and you enter mu sub 0 equals 0, and L sub 3 is what you're going to put in, which is L1 minus L2, and choose either right tail, two tail, or left tail. And of course, we're going to use a two-tail test for this. We're going to look at the same question, part B, find the 95% confidence interval. And again, reminding you that everything that we got here. I hope you realize with the two-tail test, alpha 0.05 and 95% are corresponding to each other, meaning they have the same value that we found previously. For this is 95%, the critical value left and right that we found works out here perfect. And so we are going to go with D bar plus minus E, where E is T alpha over 2 S sub D over square root of N, just like if you wrote it as X bar plus minus E, and E is T alpha over 2 S over square root of N. So we are going to replace the T with 2.120. S sub D, we have it here. Square root of N, we have it here. And we end up with 0.117. So there are two ways to write it. D bar, which is this number, plus minus this. Or we're going to say mu sub T is between this minus that, this plus that. Okay, so minus 0.906. Minus this number is minus 0.208, and plus this number is 0.268. As you can see, we go from negative to positive. That means 0 is included there. Since 0 is contained in the interval, the decision is to not reject the null hypothesis H0 mu sub D equals 0. Okay, so that is again consistent. Match T interval, you plug in the values again, and you want L1 minus L2 or L sub 3. So you can do that as well. Having said that, here's the last question. An ecologist is concerned with whether pollution entering part of a preserve area is compromising the health and growth of endangered species of snake. To determine this, he decides to measure the length of a set of mature adults from the polluted area and an unpolluted area. So length measurement for unpolluted and for polluted area. The researcher decides to perform a two-sample t-test to determine whether the mean length of these snakes differs between these two areas, and we are choosing alpha equals 0.05. So in order to do that, we have to look at a few things. The size for this group is 15, for this group is 17. The mean, add these numbers, divide by 15. For this one, add these numbers, divide by 17, and then we have the standard deviation, summation of d minus x bar, where n minus. This is x, everybody. And so we need to calculate them. We put it into a calculator. If you put that into L1, put this into L2, you can run it and you have S1, X1 bar, N1 is 15, S2, X2 bar, N2 is 17. So we did those calculations to get us ready for the next step, which is the main step, which is running the test of hypothesis. So here's the same question. Here's the information from the previous page, and here's the formula for T. By the way, you never assume equal variances unless they mention it. So I hope you remember this test statistic formula. So H0 mu sub 1 equals mu sub 2. Assume different variances, always. Okay. And so mu sub 1 equals mu sub 2. H1, mu sub 1 is not equal to mu sub 2, which makes it a two-tailed test. And that would be determining what's going on. So that would be the way. We use this formula to calculate test statistic. And so we find the x1 bar here, x2 bar here, and square root of s1 squared over n1, so on and so forth. So the given here will be put into the test statistic formula, resulting in 2.8022. Critical value comes from the choice of alpha. And degrees of freedom is, if you recall, if you go with the table, we choose the smaller of the two, n1 minus 1, which is 15 minus 1, 14, n2 minus 1, which is 17 minus 1, 16, so we choose 14. So that's how we do it when we are not using technology. So we will use a table, and t becomes plus minus 2.145. We do the graph. It's extremely important to know. This is negative, this is positive 2.145. And this number 2.8022, it's way into the rejection region on the right side. So clearly reject H0. So now, if I'm rejecting H0, loosely put, I'm not rejecting H1, I'm accepting H1, I'm accepting the claim becomes true. And restate, there is enough evidence or sufficient evidence to support the claim that the mean length of these snakes differs in these areas. It is larger in unpolluted areas since test statistic is positive. By the way, one of the things that happens, if this is negative, is smaller. If this is positive, it's larger. So having said that, let's look at technology. We're going to run two sample t-tests, okay? And we get the following. So take a look at what the result is. I've done the running. Here's the result. Look at this one. Test statistic, of course, because we use a lot more decimal, they are slightly different. But if you stop here, up to 2 decimals, they're identical. Now, degrees of freedom, we used 14. but it's almost 30, as you can see, 29.39. So it does have a different result as far as the degrees of freedom is concerned. So calculator uses different degrees of freedom because the formula d sub f, a plus b squared over a squared and 1 minus 1 plus b squared and 2 minus 1. Here's a, here's b, and degrees of freedom, if you go through this process, will be calculated. Because it's a little bit complicated, you can do with the method that was discussed. But anyways, 29. So with 29, what is the critical value? Alpha is 0.05, degrees of freedom is 29. T will be different, plus minus 2.045. However, if I put negative and positive 2.045, I put it here and here, it still keeps the test statistic in the rejection region, gives us the same result. It happened to work out the same. Furthermore, the p-value, here's the p-value here, everybody, 0.008933, and we can stop at some point, for example, stop here and change it to 9. And in a matter of comparison to alpha, which is 0.05, p-value of 0.009 is less than alpha of 0.05, so we get to the same result. We reject H0. So it's important to understand the calculated result is different because calculator uses this formula to calculate degrees of freedom. However, the result for the hypothesis testing happened to be identical. They were close enough.